All right, for part C, we'll pick up where we left off. Remember, before we were talking about specific heat and how that's an intensive property that's unique to any given substance. And in this case, since it's an intensive property, it doesn't matter how much of the substance you have. You can test any amount of substance, and if you can find its specific heat, you can line up with known values of specific heat and identify the substance, or at least narrow down the possibilities for what it is. Or if you know what it is up front, you can use the known specific heat to find things like amount of energy absorbed or released, or the mass or the change in temperature expected for a given reaction. So we saw a couple of mathematical examples of how to solve for various quantities in that equation. And for this part, we're going to start with looking at the specific heat of water. Like I said, every substance has its own unique value for specific heat. There's a table on page 238 to 239 in the hard copy, or 248 to 249 in the PDF, that gives values for specific heats for various substances. And one of them that's of a special concern to us as chemists in general chemistry would be water. The specific heat of water is 1 calorie per gram degree Celsius. That is, it takes 1 calorie to raise the temperature of 1 gram of water by 1 degree Celsius. That's the way calorie was defined originally. And in terms of joules, that would be 4.184 joules per gram degree Celsius, because it takes 4.184 joules of energy to change the temperature of 1 gram of water by 1 degree Celsius. And because the specific heat of water is relatively large, that's what makes water so good at absorbing heat. Like, for instance, from the engines in our cars, your radiator is filled with mostly water, also with some antifreeze to keep it from boiling off or freezing in the winter. But the water essentially is really good at absorbing heat from the engine. So the water comes out at really hot from the engine, goes through the radiator, and by the time it gets to the bottom of the radiator, it's relatively cool again, and it can be taken back into the engine and used to cool things down again. Unfortunately, on the other hand, that's why it takes so long to get water to boil on the stove, is because it's able to absorb so much energy with just a small change in temperature. So, kind of benefit in one way and get hurt in the other. Anyway, in practice, the equation that we just saw for C, this equation here, C equals Q over M delta T, is most often used to find Q, actually, because again, C is a unique value for every known substance. So if you know what substance you're dealing with, you know what C is, or you can look it up easily enough. And you can measure mass pretty easily, and you can measure temperature change really easily. All you need is a thermometer. But Q is the part that's hard to measure directly. And so what we usually do is we'll run a reaction in a well-insulated container, so there's no heat transfer in or out. And then we'll use this equation to find out how much energy was involved in the reaction. And again, in this equation, M would be mass, usually in grams. C would be the specific heat capacity, usually in joules per gram degree Celsius. And delta T is the change in temperature, which again is just final temperature minus initial temperature, and that would be in degrees Celsius. All right, so if the substance absorbs energy, delta T would be positive, and Q would be positive. If the substance releases energy, then delta T would be negative, and Q would be negative. Okay, so an example of what we can do with this equation, finding Q, is that, say, if a 785 grams sample of ethanol is heated and its temperature rises from 25 degrees to 78 degrees Celsius, how much heat is absorbed? And 78 degrees Celsius happens to be the boiling point of ethanol, and 25 degrees in chemistry is usually cited as being room temperature. So essentially what we're asking here is how much heat is required to heat up 785 grams of ethanol from room temperature to its boiling point. That would be another way of asking this question. Well, Q is just MC delta T. So the mass is 785 grams. C for ethanol, you can look up in the table, and it's 2.376 joules per gram degrees Celsius. And delta T would be final minus initial temperatures. That's 78 minus 25. Okay, and that's what is it, 53, well, whatever it is. And multiply the numbers together and you get 98,853.48. And for the units, notice that grams cancel with grams and degrees Celsius cancel with degrees Celsius. And so joules would be the only unit left. And that's way too, that number we got is way overboard on the significant figures. I'm going to be generous and say that this was 25.0 and that was 78.0. So we're going to use 3. You could write this down as 98,900 joules or 98.9 kilojoules. Strictly, it would be 99,000 or 9 joules or 99 kilojoules, because the way I wrote the temperatures, there are only 2 significant figures. Oh, well. Sorry. We don't always, though, use the equation in this form to find Q. That's just the most customary way that we use it. An example of how you can rearrange the equation to find other things, if you know everything else, would be looking at the check your learning question at the bottom of example 5.1. You know how they'll ask another question and they'll, similar to the one that they worked out in the example, and they'll give you the answer to the question, but they won't show you how to get it so that you can get practice working things out. Well, actually, in this case, there's a mistake in that question. So I'm hoping that nobody works ahead, or at least if you work ahead, I'm hoping that nobody tries to do that until you see this video, because they put in Q where M should go. So they've given you a mass that's actually in joules. And then down at the bottom, they give you Q, and it's the same number that they put in for the mass. And the same units, too. So it reads, how much heat in joules must be added to and this is where they put in the wrong number, gram, and the unit should be grams, not joules, iron skillet to increase its temperature from 25 to 250 degrees Celsius. And it tells you the specific heat of iron is 0.449 joules per gram degrees Celsius. Okay, so if Q equals MC delta T, then finding M, we need to get rid of C delta T. We can do that by dividing both sides by C delta T. Then C and delta T both cancel out on the right-hand side, and we have Q over C delta T would be equal to M. All right, and so M is Q over C delta T. That is equivalent, of course, to Q times 1 over C times 1 over delta T, which is the way I'm going to do it so that it's easier to see how the units work out. Q is given at the bottom of the problem where they give you the answer as 5.07 times 10 to the 4th joules. And 1 over C, C is 0.449 joules per gram degree Celsius. When you flip that upside down, it becomes 1 gram times 1 degree Celsius over 0.449 joules. And then 1 over delta T, Well, delta T, first of all, is 250 minus 25, which is 225. And 1 over that would be 1 over delta T. Notice the units, joules cancel with joules, degrees Celsius cancel with degrees Celsius, leaving you with grams as the unit for your answer, and that is a mass, so that's good. And you work it out, the 5.07 times 10 to the fourth divided by 0.449 divided by 225 leaves you with a mass of 502 grams. So that's the number that was actually missing from the problem, 502 grams. And then you could try going through, if you write that in instead of the number they gave you for the mass, you can try doing the problem again using the equation in this form to find Q, and you'll find that Q is what they gave you as the answer, 5.07 times 10 to the fourth. Okay, so you can rearrange that equation if you need to, if there's something else that you don't know other than Q. You can, as I said, since specific heat is a unique value for each individual substance, and actually it's a unique value for any given mixture also, as long as you specify the content of the mixture. So if you take something like brass, which is a mixture of copper and zinc, if you specify the percentages of copper and zinc in the brass, then that would have a unique value for Q also. But if you had a brass with different percentage of copper and zinc, then that would have a slightly different value for C. I mean, unique value for C. So if you're at a loss to say if you got a gray piece of metal and you're not sure what metal it is, it's going to be kind of hard to narrow it down just based on the fact that it's a gray metal, because most of the elements in the periodic table are metals and almost all of them are gray. So one way you could narrow it down is by, well, finding its density, I suppose. But if you wanted to do it the hard way, you could find its specific heat and match that to known values for specific heat. Better yet, you could find its density and its specific heat and match both of them. And if you get both of them to match, then that's a pretty good indication that, that's what it is. So an example of doing that would be, say, if addition of 641.5 joules of energy to a 100-gram piece of metal causes its temperature to rise by 27.3 degrees Celsius, is the metal silver or iron? And what you're going to do is find the specific heat for this metal and see if it matches the specific heat for silver or the specific heat for iron. Specific heat for silver is 0.235 joules per gram degree Celsius, and the specific heat for iron is 0.449 joules per gram degree Celsius. Those are far enough apart that even allowing for some experimental error, you should be able to tell the difference between the two. I mean, that's assuming that we were actually doing the experiment instead of a calculation. So Q is equal to MC delta T. That, hopefully, we know by now. If you want to find C, that means you have to divide the right-hand side by M and delta T, and you have to do the same thing to the left-hand side to keep it equal. M and delta T will then cancel out on the right-hand side, and so you have Q over M times delta T is equal to C. And that's what we get here. C is equal to Q over M delta T. Now, of course, in order to work out the units, I'm going to make this Q times 1 over M times 1 over delta T. And so that's Q is 641.5 joules. 1 over M would be 1 over 100 grams. And 1 over delta T would be 1 over 27.3 degrees Celsius. And if you look at the units, you'll notice actually none of the units cancel out. But what the units you do end up with will be joules over grams times degrees Celsius, which are exactly the units we want for C. So that's good. When you do the math, you get 641.5 divided by 100 divided by 27.3. You get this long, ugly number here, which we cut down to 3 significant figures because all the smaller numbers in the problem were 3 significant figures. And you get 0.235 joules per gram degree Celsius, which is the heat capacity, or specific heat for silver. So the metal was silver. Of course, another way to tell the difference would be just throw some salt on top of the metals and see which ones rust. All right, so that's a way that you can identify an unknown metal, or an unknown substance for that matter. The next part is section 2. There are only 3 sections in this chapter, so we're already on section 2. So it's going pretty quickly so far. So like I said, be sure that you get right on the homework problems as soon as I post them. The subject of section 5.2, which starts on page 242 in the hard copy and 252 in the PDF, is calorimetry. Calorimetry, it literally means measuring heat, because calor comes from the Latin word for heat, and the metry part comes from the Greek and Latin words for measuring. So essentially what we're doing here is measuring heat. Calorimetry is the type of experiment that we do in order to get these numbers that we've been using in these examples so far. What we desire to do is to make things simpler for ourselves. We're taking advantage of the fact that the amount of energy in the universe remains constant. In other words, energy can't be created or destroyed, but it can be changed in form, and it can be moved from one place to another. So any energy that's given off by a chemical reaction has to be absorbed by the environment, its surroundings. Any energy that's taken in by a chemical reaction has to come from the surroundings. And if we want to get accurate numbers for doing the kinds of problems that we've been doing so far, though, we have to take certain steps to make things a little bit easier. Otherwise, things can get really complicated really fast. If you're doing a reaction trying to measure Q, or to find a change in temperature in order to calculate Q, and you're doing it just in a beaker sitting on a counter in the lab, then okay, the chemical reaction gives off some energy, gives off some heat. That heat will be taken in by the surroundings. Well, what are the surroundings? The surroundings would be everything else in the universe, essentially. Okay, so Pluto is not gaining much energy from your little chemical reaction going on the benchtop in the lab, but it's still pretty complicated, because the surroundings would include not only the solvent. Say if you're doing the reaction in water, water would be part of the surroundings. Your thermometer would be part of the surroundings. The beaker would be part of the surroundings. The counter under the beaker would be part of the surroundings. The air all around the beaker would be part of the surroundings. The air above the beaker would be part of the surroundings. You're part of the surroundings. And you're starting to see how complicated this could get. So what we do in experiments like this is we use an insulated container. We conduct the chemical reactions or the physical process inside a container which is thermally insulated from the outside. In other words, inside a container, kind of like a thermos, where there's no transfer of heat in or out, at least not during a reasonable period of time for our reaction to occur. Once we do that, that calorimeter becomes the universe, okay? Because it's isolated thermally from the rest of the universe. The word insulate comes from the Latin word insula, which means island. So basically, when you insulate something, you're cutting it off thermally from its surroundings, kind of like an island is cut off from other land. So now the universe is inside that calorimeter, is sort of a new semi-universe. And any heat transfer in or out is confined to the limits of that calorimeter. So now the chemical reaction, if it gives off energy, the surroundings will absorb that energy. And now the surroundings consist of nothing but the solvent, which is usually water, and the inner surface of the calorimeter. And if you want to be super accurate about it, the thermometer and the air above the solution inside the calorimeter. Those last two are small enough that they can usually be ignored. So now you really only have to account for the heat that's being absorbed by the solvent, which is usually water, and the inner surface of the calorimeter. That's two things down from practically an infinite number of things if you were not doing it inside a calorimeter. Even better is if you're doing it in something like a styrofoam container, because styrofoam basically doesn't absorb any heat at all within a reasonable length of time. So if it's a reasonably quick reaction, you can do it in something as simple as a styrofoam coffee cup, and you don't even have to worry about heat that's absorbed by the inner surface of the calorimeter. All you'd end up having to worry about would be the heat that's absorbed by the water. And so it really simplifies things hugely. All right. If you're using a commercial calorimeter and not, just a styrofoam coffee cup, the heat capacity of the calorimeter is usually known in advance. Sometimes the manufacturer will tell you what the heat capacity of the calorimeter is, although you should really only use that number when the calorimeter is relatively new, because as the materials it's made of get used over and over again and they can deteriorate somewhat over time, that number could change. So if you don't know what the heat capacity of the calorimeter is, or if it's old, then you end up having to find out what the heat capacity of the calorimeter is, and that itself can be kind of a pain. And so, like I said, if the reaction is fairly quick, you're probably better off just doing it in a styrofoam cup, because for a fast reaction, the styrofoam is really not going to absorb any heat at all. And it won't give up any heat at all. So for any thermal process, whether it's a chemical reaction or a physical change, like dropping a hot piece of metal into cold water, that would be a physical process. We have to distinguish between what is actually gaining or losing the heat versus everything else. So the system, what we call the system, consists of nothing but the substances absorbing or releasing heat. If we're doing a chemical reaction, then the system would just be the reactant molecules and nothing else. Not the water, not the solvent, not even the product molecules, just the reactant molecules. Okay. The surroundings would be everything else. And that would be the solvent, the container, the thermometer, the air above the solution in the container, and the rest of the universe. But like I was saying, if you're doing it in a calorimeter, the rest of the universe part, you can ignore that. And in fact, in most cases, you can ignore the air and the thermometer also. And then you just have the solvent and the container. And if you're doing it in a styrofoam cup, you can usually ignore the container too. If the reaction is exothermic and it occurs in a calorimeter, then that means that the heat is going to be released by the system, that is the reactant molecules, and the heat's going to be absorbed by the surroundings, and that would be the solution or the solvent, and the inner surface of the calorimeter and the thermometer and the air. Although, as I said, thermometer and air can usually be ignored. And if it's in styrofoam, then you can even ignore the inner surface of the calorimeter. So principally, what's absorbing the heat given off by the reactants would be the solution or solvent. In most cases, that would be water. If the reaction is endothermic, then, and it's done in the calorimeter, then the system absorbs heat. That is, the molecules of the reactants are taking in heat from the surroundings, and the surroundings would be releasing or losing heat. And again, the surroundings would be principally the solution or the solvent, usually water, but also the inner surface of the calorimeter if you're not using styrofoam, and thermometer and air, but again, we can usually ignore those. In most cases, we follow the progress of the reaction by monitoring the temperature of the solution or the solvent, which is part of the surroundings. So this creates a bit of a contradiction here, because the convention is that we always follow the reaction from the point of view of the system, from the reactant molecules, in other words. But we're actually monitoring the temperature of the surroundings. So if the thermometer goes up, that means the surroundings have gained energy, but it means the system has lost energy. And if the thermometer goes down, that means the surroundings are losing energy, but it means the system has gained energy. So things are kind of backwards that way. So if the system releases energy, that is, it's an exothermic reaction, the solution or surroundings will gain energy and the temperature increases. So if the temperature goes up, or in other words, delta T is positive, the reaction is exothermic and Q is negative. If the system absorbs energy, that is an endothermic reaction, the solution and the surroundings will be losing energy and the temperature decreases because the thermometer is part of the surroundings. So if the temperature goes down, or in other words, if delta T is negative, then the reaction is endothermic and Q is positive in that case. So then we can use delta T along with the mass and the specific heat of the solutions or the solvent to find Q. There are some diagrams of the calorimeters in the book. Actually, 511 is more of a schematic diagram just to show you what goes on inside of a calorimeter. Figure 512 is a diagram of a styrofoam cup being used as, they refer to it as polystyrene in the text. I'm not sure why. I mean, styrofoam is polystyrene with air pumped into it. Styrofoam technically is a brand name, so maybe they were afraid of getting sued or something. But styrofoam cup, interestingly though, they use styrofoam in the diagram, so I don't know what's going on. The figure is 5.12 on page 244 or 254, depending on which version of the book you're looking at. It's very simple. It's really just a styrofoam cup with like a cardboard lid on top and a hole in it for the thermometer, and the reaction goes on inside the cup. The styrofoam, like I said, basically absorbs no heat during a reasonable length of time. Eventually, it will absorb some heat, but not right away. And so that's really the easiest way to do experiments like this. If you need extremely accurate numbers, though, then you can use professional calorimeters. Some of them are really fancy and really expensive, like the one on page figure 513, rather, on pages 245 or 255. That shows you a fancier setup. But the downside to that is you would have to know what the heat capacity of the calorimeter is before you could actually get any reliable results out of it. Okay, so calorimetry can be used to measure heat transfer. Heat transfer always occurs from warmer areas to colder areas, remember? So for example, like from hot metal to cold water, or from higher energy reactants to lower energy products. And you basically, you could also do this, an experiment like that. Dropping hot metal into cold water could be used to find the heat capacity of the metal, and from there to identify it. And along those lines, that is like dropping a hot piece of metal into cold water and finding the heat capacity in order to identify the metal. Since the total change in energy, that's delta E is change in energy in the universe, has to be 0, and in this case, the calorimeter is the universe, then what that means is that the amount of heat released by the metal plus the amount of heat gained by the water must be 0. Or in other words, those two quantities must be the same in magnitude, although opposite in sign. So whatever amount, if the metal releases 500 joules of energy, then the water is gaining 500 joules of energy. So another way of saying that is the negative of the number for the number of joules released by the metal would be equal to the positive of the number for the number of joules gained by the water. And since Q equals MC delta T, I changed the signs around here, so I'm going to just fix that. Okay, since Q equals MC delta T, that would mean that Q released by the metal is M metal times C metal times delta T metal. And Q gained by H2O would be MH2O, CH2O, delta T H2O. And from all of this, you can, and remember there's a negative sign there, from all of this, you can solve for the C of metal. You just have to divide both sides by M metal times delta T metal to get those to cancel on the left-hand side. And so you end up with the negative of mass of water times the specific heat of water times the change in temperature of the water over mass of the metal times the change in temperature of the metal. And if you work that out, the mass of the water and the metal, you would have to know, would have to be given to you in a problem. And the changes in temperatures would have to be given to you also. The C of H2O you can look up, that's 4.184 joules per gram degree Celsius. And from that, you can end up with C of metal. And this negative sign really needs to be there because one of these delta T's will be negative. It'll be actually the temperature of the metal. Since the metal was hot to begin with, it's going to cool down. That's a negative delta T. So you're taking, so that would make this whole quantity here negative, and you're taking the negative of that, which would make it positive, because specific heats are always positive. Okay, and well, next time, I see we're a little over time on this, but next time I will show some examples of that. Okay, so gives you something to look forward to. I'll see you next time, and I'll have those homework problems up soon.